I have talked about first law and second law and their applications and Cauchy's inequality and all. So today's lecture, I concentrate first on combining first and second law. So what we would like to do is we want to combine. So second law gives you the definition of entropy, and also it tells you that del Q reversible equals to T dS. Now, if I want to combine it, my first law is du, which is the change in internal energy, is equals to delta Q reversible plus delta W. And delta W, if we only consider mechanical work, reversible mechanical work, is minus PdV. So then you have minus PdV, delta W, and delta Q equal to TdS from the second law. So, and remember that delta Q reversible is equal to TdS, and ds is greater than equal to delta Q by T, which is Cauchy's inequality. Now, once you combine this, what you get is, basically if you combine this, you get du equals to TdS, right? TdS, which is delta Q minus PdV, right? So you get du equal to TdS minus PdV. Now, since u is a state function, it's an exact differential, right? So we can write du as del u del s at constant volume ds plus del u del v at constant entropy dv. Now you have del u del s at constant volume. This is partial derivative of u with respect to entropy s, and this is partial derivative of this one is partial derivative of u with respect to volume. Partial derivative of u with respect to volume, and this is also taken at a constant entropy. Now, if I want to combine, if I want to compare with this du equals to TdS minus PdV, what I get is del u del s. Del u del s, constant volume, is nothing but temperature. This change in internal energy, change in entropy, is basically giving you a definition of temperature, right? T equals to, if you look at this, if you compare them, del u del s V is equal to T, del u del s V equal to T, and del u del V S equal to P. So at constant entropy, you can write that pressure is nothing but the change in internal energy, change in volume, right? At constant entropy, that is the pressure, and there is a negative sign here, and you can again understand it from this very simple idea that as you increase as you reduce the volume, as you apply external pressure to a system, the volume is reduced, right? So you will get a change. The change volume will be negative. So you have to put a minus PdV so that delta W, that is work done on the system, is possible. So you have T, which is equal to del u del s V, and minus P, which is equal to del u del V, right? Also, previously we have noted that there is one new thermodynamic variable we defined, which is called enthalpy or heat content, which combined U as well as P. So now, if I do dH, we get du plus PdV plus VdP, right? Because PdV plus VdP. Now at constant pressure, dP will be 0, right? At constant pressure, dP will be 0. So dH is also basically, so del H del dP, right? If you remember the definition of Cp, Cp is del H, change in enthalpy respect to change in temperature at constant pressure. So dH is basically Cp dt, which is du plus PdV, and du is Cv dt, right? So now, using the combined law, we will try to find out a relation between Cp and Cv. We have already given that relation between Cp and Cv in terms of Cp minus Cv was a function of T, V, alpha, beta, right? We will try to prove that, we will try to derive that using the combined statement of first and second law, right? This becomes a very important exercise, and by the way, you can do it for various other relations, and these you get many useful thermodynamic relations. By the way, I will introduce later Maxwell's relations, which talks about the second derivatives, and we will use some of it here. However, we will show more systematic way of deriving these Maxwell's relations and applying them to find relations between different thermodynamic properties, right? But here we will tell that the combination of first law and second law gives you a way to derive this relation, the generalized relation between Cp and Cv for any material, whether it's a gas. Before we have defined Cp minus Cv equal to R only for ideal gas, right? Now Cp minus Cv, here we will try to, or Cp minus Cv equal to Nr, where N is the number of moles, and if I don't think of molar heat capacity. So, but Cp minus Cv is a function of temperature, volume, alpha and beta, and we have also shown that that expression boils down to the Cp minus Cv equal to R for ideal gas, for ideal gases. If you think of Cp as the molar heat capacity at constant pressure and Cv as the molar heat capacity at constant volume. Now, if you want to use, so this is the statement, the problem statement. Let us write the problem statement, that use the combined first law and second law of thermodynamics, right? Use the combined first and second laws of thermodynamics. Basically use this expression du equals to Tds minus Pdv to prove Cp minus Cv is Tv alpha square by beta. Okay, so this is the relation that we want to prove. Now, one thing is that whenever you have whatever is a state function, that state function will basically give rise to an exact differential. So basically I can write this way, I can write different relations. Say for example, I can write volume as a function of temperature and pressure. I want to express volume as a function of temperature and pressure. Now, if we use exact differential, right, because volume is an exact differential, volume is state function, so it's an so we can write as an exact differential. So if we express the differential in volume as an exact differential, we get, and with t and p as the independent variables, right? V is a function of t and p are the independent variables, V is a function of that, and so what you get is del V del Tp dt plus del V del Pt Tp. Now alpha, which is the volumetric coefficient of thermal expansion, is 1 by V del V del Tp, right? That is something that we have defined previously. And beta is isothermal, so this is volumetric coefficient of thermal expansion. So I just write it bigger here. So alpha, the volumetric coefficient of thermal expansion is alpha, which is 1 by V del V del T, the partial derivative of V with respect to temperature at constant pressure, and beta is isothermal, right, because it's at a, as you can see, del V del P at a constant temperature. So isothermal compressibility. And note the minus sign here, right? You should not forget the minus sign here. Normalize with volume. So del V del Tp basically means V times alpha. So it becomes V alpha dt. dV equals to V alpha dt minus V. So here there is a mistake. Should be del V del Pt is nothing but minus V beta. So minus V beta dP. V alpha dt minus V beta dP. Okay, where del V del Tp, as you can see, is V alpha and del V del Pt is minus V beta. So you can see that V as a function of temperature and pressure gives you this relation V alpha dt minus V beta dP, where dV is expressed as an exact differential, and in that exact differential the independent variables we have taken as temperature and pressure. So we can take any state function to be a function of some other variables that are again state functions themselves, and we can express such relations, right? We can find these definitions and we can apply them, right? So that is something that we will do. So for example, here Cp is written in terms of change in enthalpy with respect to change in temperature at constant pressure, right? Del H del T P. Cv is change in internal energy with respect to change in temperature at constant volume. And as we know that the enthalpy is H equals V plus PV. So now if I take a differentiation, so if I divide by dt, so it's like I am dividing this dH, which is du plus vdv plus vdp. I am defining this relation. So first what I have done, from here write dH, which is equal to du plus vdv plus vdp, and now I divide both sides with dt, right? I divide both sides by dt, right? So we get dH dt equals to du d by dt equal to plus p dv by dt plus v dp by dt, and now I consider isobaric conditions, that is dp equal to 0. So what you get is del H del Tp equal to del U del Tp, right? Del U del T, change in internal energy with respect to temperature, constant pressure. This is something that is unknown, right? We don't really know this, right? We know del U del Tv, but we do not know del U del Tp. Plus, because it's a constant pressure process, so dp dt, the term will go, right? dp is equal to 0. So p del V del T at a constant pressure. Now del V del Tp is something we already know, right, in terms of alpha, right? 1 by V del V del T equal to alpha. So we will now we will take now another expression, again I will relate one state function to another, a combination of other state function variables. So we will relate U to volume and temperature in the next step. So in the next step, so you have this equation del H del Tp, which is Cp, equals to del U del Tp, which you do not know, and P times you have del V del Tp. Del V del Tp you have seen previously is related to alpha, V alpha. This is basically V alpha, right? So this is basically, it becomes P times V times alpha. This is Cp, but this guy don't know, right? This term don't know, right? You are now taking this expression U equals a function of V and T. Now if you take U as a function of V and T, so you are taking here, it is following from U is equals to U as a function of V, which gives you du, which is del U del V T dV plus del U del T V tt, right? Del U del V T, right, at constant temperature. So this is the partial derivative of U with respect to volume, change in volume at constant temperature. By the way, for ideal gases this term goes to 0, right? For ideal gases where there is no interaction between the molecules, this term goes to 0. But you have del U del, so but in general it is del U del V T and this is del U del T V and T. Now if I again use constant pressure and divide 2, that is this equation 2 by dt and take P constant, right? So divide 2 by dt and take P constant, what I get is del U del Tp. See, I want to find out del U del Tp. So del U del T at constant pressure equals to del U del V at constant temperature times del V del T, right? dV by dt at constant pressure will be del V by del T at constant pressure, right? From here I get it, because I am dividing dV by dt and take P constant. So this becomes a partial derivative del V del T P plus del U del T. So you have del U del T V and dt by dt is basically you can just cancel them out, right? So so you have only del U del T V left. Now you have 3 here. So this is equation number 3. This is equation number 3. Now substitute this result into the result 1, right? So you have del U del Tp. This is where we substitute this relation del U del Vt, del V del Tp and del U del Tv, and then we see. So 1 is exactly, so I have written 1. This is again I have rewritten the expression, that's why for your convenience. Now this del u del t p, I have written this expression. So now take the right hand side and put it here. So this term is substituted by this entire term, right? This entire term substitutes this term. Now if you do that, what you get is del h del t p equals to del u del v t times del v del t p plus del u del t v, right? Plus del u del t v plus this term p del v del t. So now you get another expression where del h del t p is Cp, del u del v t is Cv, and there is del u del v t which is del u del v t which is not Cv. So sorry for this. So del u del t v, there is one term del u del t v here which is Cv. So let us write this way. Put this. So this one I will substitute as Cv. Del u del v t, we have to find out what is del u del v t, and if you remember del u del v, we have done it previously when we equated the combined first law and second law, and we equated the exact differential form of du. We found del u del v s, right, equal to minus p. So we have to now find out what is del u del v t. Okay, so del u del v t, which is pi t, right? We call it pi t, which is like the internal pressure coefficient, right? So this is something we want to find out, right? So we are trying to find out. So here we have represented this as Cv. Now you have this p del v del t p, right? Del v del t p is again a function of its v times alpha. So v alpha here comes. So here it is. So now if you see, there is a v alpha term here, right? This is v alpha. This is also v alpha. So I take v alpha common, then I get p, right? I get p. And I get del u del v t, right? Del u del v t. We know del u del v s, but we do not know del u del v t, right? And v alpha is common, and v alpha if I take common, then we get p plus del u del v t, and del u del t v is the changing internal energy with temperature at constant volume, which is C. So Cp equals to Cv plus this, right? This is 4. Now once you have done this, you have got du which is Tds minus Pdv, right? Du is Tds minus Pdv. You have got this relation, and now you see, and du is also this del u del tv and del u del vt dv, right? So now you have one very interesting way of writing this first second law combined. So this is the combined expression for first and combined first and second laws. You should do it independently, and you will see that once you do it, there is a sequence here. You will be able to follow the sequence. So here, what we have, because you remember that we know about del u del v s. Del u del v s give me minus p, right? But I don't know del u del v t, right? We know that is pi t, but pi t is something that does not appear in the expression that we were trying to find out, right? There is still no beta in our expression, right? So that is something that we have to think of. Now what I am doing is, I rearrange this statement. This combined first law and second law. So ds is something that I take out. So then this becomes ds is, so I can divide all sides by t. So this becomes du by t equals to ds minus p by t dv. And then if I rearrange, so I get ds equals to du by t plus p by t dv, right? 1 by t du plus p by t dv. Now again let us look at it. So you have 1 by t du, and du is del u del t v dt, right? Del u del t v dt plus 1 by t del u del v t dv plus, right, and plus p by t dv, right? You have three terms now because du, I am using this definition of du here, this du, I am substituting, right, this expression, right? So instead of du, I am writing del u del dv dt, right? So this is the expression that I am substituting, right? So it becomes 1 by t del u del t v dt plus 1 by t del u del v t dv plus p by t, there is a plus p by t dv, right? The p by t dv comes from here, right? When I arrange ds in terms of du and v, right? That's what I am writing. So what I get is 1 by t del u del dv dt, that remains, and here I take again 1 by t common and I see p plus del u del v dt, that is equation number 5. Del u del v, change in internal energy, just change volume as of at a fixed temperature. Now you see, this is something again comes back, right? Now let us look at, now again I will take another, so again I can express now s, because s as a function of t and v. Remember, the objective is to basically not to find del u del v s but del u del v t. So that is why we are making so many different, invoking so many different expressions, so many different dependencies, and we are trying to basically make sense. So all this will make sense once you start looking at the relation between the second derivatives also, or the Maxwell's relations also. But so I just want to tell you, say for example, the way we started is like we started with the definition of u as a function of v and t, right? And we had the we started with the expression of dh dt, right? Where because del h del dp is the cp. So and then we invoked u as a function of v and t, and then we invoked, after that we have invoked s as a function of t and v, right? So s as a function of t and v. So u as a function of t and v and t gave me equation 4, and then again I readjust, means rewrote the combined first and second law statement in terms of ds, right? Ds on the left hand side and the rest of terms on the, so it is in terms of s as a function, right? Ds as a function of du and dv is what we have written, and now we want to find the relation between s and temperature and volume. Temperature and volume are independent variables here, and s is dependent on t and v. Again, s being a state function, we can now write it again as an exact differential. Now you can see why I am doing this. You can immediately see, we equate the coefficients, right? We have shown that from the combined first and second law, you got du equals to pds minus pdv, and then from the exact differential definition, you got del u del tv and del u del del u del v s and del u del s v, and del u del s v, for example, we equated to temperature, right? Del u del s v was temperature, and del u del v at a constant entropy is basically minus p, right? So this is something that we could easily find out. So here now you can see what are the derivatives, del s del t v and del s del v t, but we have already got ds as a function of dt and dv, right? If you look at equation 5, ds is a function of dt and dv, and what are the coefficients? 1 by t del u del tv, and another case 1 by t p plus del u del v, right? Now if I compare 5 and 6, right, we get del s del tv is nothing but 1 by t del u del dv, right? And del s del vt is 1 by t del u del vt plus p, right? So these are the two expressions that you are getting by comparing 5 and 6, right? Now this is something that I want to tell you. Now comes this relation, the basis of Maxwell relations, and that is, if you have an exact differential dz, right, dz which is a function of z, so it comes from z being a function of x and y, and so we are writing here dz equals to m dx plus n dy, and m is nothing but m is del z. So m is what? M is del z by del x at constant y, and n is del z by del y at constant x. What do we see here? And that is the property of an exact differential, that del m del y equal to del m del x. That means del 2z del y del x equal to del 2z del x del y, right? So this is the property of an exact differential, right? Del 2z del y del x. So the order of differentiation in the case of second derivative does not matter. Del 2z del y del x is equal to del 2z del x del y. We will just use this identity here, and therefore if we use this identity for s as a function of p and v, we can write del 2s del t del v is equal to del 2s del t del t. So del v of del s del t v is del t of del s del v, right? Now del s del t v we have already found out, right? Del s del t v is basically 1 by t del u del t v, right? So we are writing del v of 1 by t del u del t v because del t of del s del v t also we have found out is p plus del u del v t, and there is a 1 by t in the front of the bracket, right? 1 by t del u del v t plus del u del v plus p by t, right? We have taken t inside, and then this is del t. So what we get is 1 by t, if I take it out from here, I take out 1 by t here, so it becomes del 2u del v del t is equal to, I take 1 by t here out, so it becomes, so here basically I am using the chain rule, right? Del t, so if I take, in the first case I am writing 1 by t, I am taking it out, and I am writing del 2u del v del t plus del p del t v, and with a common 1 by t, and the other one is this term del v del v plus p remains as it is, and you have minus 1 by differentiation of 1 by t with respect to t will give you minus 1 by t square, right? So what I get here is this expression, right? So 1 by t del 2u del v del t, and there is 1 by t del 2u del v del t again, right? You have these two terms, right? So if you expand, you get 1 by t del 2u del v del t here, 1 by t del 2u del v del t here, which you can basically cancel. So what are the terms that are remaining? You have 1 by t del p del t v, that term remains, equal to 1 by t square del v del u del v. Remember, this is del u, this is u, right? Del u del v t plus, right? 1 by t square del u del v t plus p is 1 by t del p del t. That's what we are writing, right? 1 by t del p del t v, because you see the secondary term, this term, and this term cancels, right? Now you get 1 by t del p del t v equals to 1 by t square del u del v p del u del v t. Note that this is t, right? Del u del v t plus, so t del p del t v, so equal to del u del v t plus p. Now you see some familiarity immediately, because del u del v t is something you know, which is minus v beta, right? We already know that, right? Del u del, not del u del v, sorry. So this will be del v, the beta is again minus 1 by v del v del. I still want this relation, so it's still a little bit far away. So right, 1 by v change in volume with respect to change in pressure at, this is isothermal, so at constant temperature, right? So this is not what it is. So we still have to wait a little bit. So we now know t del p del t v, but the good thing is now we know del u del v t. Del u del v t is t del p del t v, right? Changing pressure with respect to changing temperature at constant volume minus p, right? This is equation number 7. This is your equation number 7. Now again I invoke, and we have to, so we have P and T and V as a function of T and P. So if I write that, then dV equals to del V del P T dP plus del V del T P dt, which we have already written, right? So now if V is fixed, now is the thing. So it is basically say for example like an isochoric process. So where dV is equal to 0, right? If V is fixed, volume is fixed, volume cannot change. So in that case, dV becomes equal to 0 and del V del P T dP equals del V del T P dt, and now what you get, which is basically del V del P T, and if I divide by dt for example and at constant volume, so it becomes del P del T. So this term becomes del P del T V, and this is del V del T P. So del P del T V, so this is where this del P del T V term that we have, this del P del T V term is what is used, and this is nothing but minus del V del T P by del V del P T. Now this del V del P T term basically gives you minus V beta, right? So this gives you minus V beta, and above there is a V alpha and there is a minus sign. So minus minus becomes plus, and so this del P del T V becomes equals to alpha by beta. Now you have got the expression that you want to use, because you now have Cp plus Cv, what we Cp equals to what we have got previously. Let us look at the Cp equals to Cv plus V alpha P plus del U del V, right? That was the expression. And then we also found del U del Vt, so that is equation 7 equals to T del P del Tv minus P. Now del P del Tv is what we have used as alpha by beta. Now we can now put all of this together, so it becomes Cp plus equal to Cv plus V alpha P plus del U del Vt, and del U del Vt is again coming from T del P del T at constant volume minus P, right? So now P and P, as you can see, cancels up. So you have T del P del Tv here and you have V alpha here, and T remains, but del P del Tv we have found out to be alpha by beta. So if we put all of this together, we basically get Cp equals to Cv plus Tv alpha square by beta. And this is the relation between Cp and Cv for any material. And this is something that you will be using. But however, you have used from there, if you take what is alpha for the ideal gas and beta for ideal gas, if you remember, you got Cp minus Cv. If it is a 1 mole of ideal gas, it is equal to 1, right? If you take alpha and beta, by the way, in alpha for ideal gas, try to find out what is the relation between alpha and temperature, and what is the relation between beta and pressure for an ideal gas. Then it is something that I have proved already, so you can check that. I don't want to repeat it here, but you can see that you invoked multiple relations. However, one of the central relations that you started with was the combined first and second law. So combined statement of first and second law is important to understand the relations between different thermodynamic properties. And remember, this is something that is very, very useful when you also want to express or want to find indirectly measurable thermodynamic quantities, for example, the S or U in terms of measurable quantities such as Cp, Cv, alpha, beta, temperature, right? Temperature, volume, pressure. Okay, so that is one thing that immediately follows from the combined statement of first and second laws, right? So there are several such relations that we will explore later, and this is something that you have to remember, that whenever you use this combined statement, you will get you can arrive at these relations. However, it takes some sort of thinking about the relations, and obviously it requires some algebraic manipulation. It's not always easy to remember this, and you require to do a little bit of trial and error. That is also true. But once we use Maxwell relations again, it may become slightly easier for you to find these relations. However, as you can see, it does require a little bit of algebraic manipulation and a little bit of patience, because you have to basically find out what are the relations, particularly what are the partial derivatives that we want to really find. So for that, what type of dependency we should consider, right? We know the properties of exact differential, but how to use that to get into these relations? It is always possible, for example, to use a simpler way to arrive at the same relation, right? The relation that I have arrived at, you can arrive at it in a simpler way. That is always possible, right? By using a different combination of variables. Now, as you know that for any given phase or any given system, right? For example, liquid water, or whether it is solid silver or silver in the molten state, or whatever it is, you can write this type of relations, right? So this type of equations, and these equations are generally found from experimental data, right? CPT. So please note that for a given, this is always for a given phase. For example, if it is liquid water, I have a dependency of heat capacity at constant, heat capacity as a function of temperature, right? Heat capacity as a function of temperature. And this relation involves these coefficients like A, B, C, D. So it can be also much more complicated in terms of Cp and temperature dependence. The point is that once you have this relation, these relations are derived from experimental data, and these are derived for a given phase, right? The experimental data, the data that you obtain from calorimetry, and from there you can express you can find out the values of A, B, C, and D, and this is something that we often use to find out, right? To find out the change in entropy, for example, right? Change in entropy. How do you find change in entropy? It's very simple. You see, delta Q equals to TdS, that's we have written, right? Delta QP reversible. So it is delta QP is the heat transfer at constant pressure. At constant pressure means it is equal to dH, right? Equal to dH, which is Cp dt, right? dH becomes equal to Cp dt because dH equals to du plus dV, right? At constant pressure, and if it is so, which is equals to delta Qp, and which is nothing but Cp exchanging velocity. And here we are using, because it is constant pressure or isobaric, therefore we are using Cp, that is heat capacity at constant pressure. Now, dH equals to Cp dt basically now gives you an idea, because del Qp is also equal to TdS. This is also equal to TdS. Now, therefore, it immediately gives you an idea to measure entropy or to find entropy or change in entropy as a function of Cp and T, right? Cp and T are measurable quantities. These are directly measurable quantities. T you can use thermometer, Cp you can use a calorimeter. So calorimeter gives you Cp, it gives you even the temperature dependence of Cp. And now if you know this relation Cp dt equals to TdS, that means ds equals to Cp dt by T, right? ds equal to, that's what I have written, ds equal to Cp by T into T. So if I do this integration from some temperature, initial temperature to some final temperature, I can basically find out the change in entropy, because change in entropy cannot be directly measured, but change in Cp can be measured, right? Change in Cp can be measured, Cp can be measured itself. So because, see, for example, this is an empirical relation, right, between temperature and heat capacity, and this empirical relation is derived from experimental data of experimental data from calorimetry, right? And you also know how to measure temperature. So if I know the initial temperature and final temperature, I can find the change in entropy. So this is how we can measure the indirectly measurable quantities like delta S or delta U, correct? So for example, this is again, please note that when you use these relations, when you use these parameters A, B, C and D, make sure that you are doing it in the applicable range. For example, for silver solid, A is 21, B has a unit of 1 by Kelvin, which is 8.5 × 10⁻³ and C has a unit of Kelvin square, right? C by T square, so it has a unit of Kelvin square, and it is 1.5 × 10⁵, and D T square, D is not reported, so A, B, C are sufficient for silver solid. But note that the temperature range in which it is applicable is 298 to 1234 Kelvin. So therefore, if you want to see a change in entropy in these temperature range where the process involves solid silver in some way, then basically you can use this relation, but always note the applicability in the temperature range. In these temperature range only this A, B, C values are valid, right? For example, nickel liquid has only A, right, which is constant basically, but the constant is between 1728 and 1900 Kelvin. So between 1728 and 1900 Kelvin, 1728 Kelvin to 1900 Kelvin and 1900 Kelvin, this nickel, liquid nickel or molten nickel has a constant heat capacity at constant pressure, right? So heat capacity, the heat capacity is at constant pressure is constant. By the way, this is something that you can prove, and you can show that the Cp and Cv in case of solids and liquids. This is something I have already given an example. Even in assignment, I have given a problem like that. So you will see that the difference in Cp and Cv becomes much less and often negligible when it comes to phases like when it comes to condensed phases such as solids and liquids. But you have to also understand that it depends on the problem for which you want to neglect the difference between Cp and Cv. So please read the problem statement carefully and see in that problem statement, is it okay to neglect the difference between Cp and Cv, because sometimes the Cp and Cv difference, if it is purely condensed phases, sometimes it is possible that there is some difference and that difference cannot be neglected for a particular type of problem where the range is such that if you neglect this the difference, you may actually get a large error in the outcome, right? So if the difference is like 1% or 2% or 5%, in some cases it is okay to neglect, but in some cases it becomes very difficult to neglect such differences. Okay, so it depends on the problem where you want to say, okay, Cp is nearly equal to Cv for solids and liquids. Okay, so this is something that you should always take into account. Now think of a process where there is phase change. For example, if you have a phase change, say you are constantly giving heat to the system, and the system starts with a solid. Now the solid is basically, so you can think of some origin, you can think of the origin to be at 0 Kelvin, origin to be 298 Kelvin, right? So there is a special property of entropy, that is what I am going to express soon. And before that, that's what I wanted to tell you, that what is your origin depends on the choice relevant to the problem, right? If you think of entropy, you start from 298 Kelvin and you start hitting, and we are hitting the solid, and the solid then transforms to liquid. Now one interesting thing, and this is something all of us know, that there will be a temperature at which solid and liquid are in equilibrium, right? That is called the melting temperature, at which solid and liquid are in equilibrium, right? And when solid is transformed to liquid, then instead of looking at the sensible heat which is given by Cp dt, you look at something called latent heat, right, or enthalpy of transformation, right? So that is something that we have already talked about. So enthalpy of transformation is something that you have to invoke here. Now when you talk of enthalpy of transformation, one thing, you have this, in the solid liquid equilibrium case, you have this heat input, you continue to have this heat input, but there is no change in temperature, right? There is no change in temperature that in this equilibrium process, right? When you have solid liquid, once it changes to completely liquid, again you can see you can estimate the sensible heat. Otherwise it is called, that's why it is called latent heat, right? So in solid liquid, the temperature remains fixed, right? This is at the melting point. So this point basically is a melting point. In fact, if you go the other way, then it is also called the melting temperature or solidification temperature or fusion temperature, right? Temperature of fusion, at temperature at which the solid melts, or temperature at which the liquid solidifies, and that is the temperature where solid and liquid are at equilibrium, right? Again, you start with the liquid, go up. So as it is going up, it should go up. So as it goes up, then liquid converts to vapor. So again, there is another equilibrium, and that is the equilibrium which is given by the boiling point, right? So that is the liquid changing to vapor. So it is called the boiling point. Boiling point, or you can think of like condensation point, right? Vapor condenses to, right? Again, at that point, you have only the heat of transformation, right, or latent heat. Evolution, right? So, for example, if I want to convert solid to liquid, then the solid has to absorb some amount of it, right? So it's an if solid absorbs it, so it is an endothermic process. And but when, on the other hand, when liquid solidifies to a solid, then liquid releases it, so it's an exothermic process. So similarly, you can do it for liquid to vapor transformation, right? So at liquid vapor transformation, again the temperature remains fixed. Now that all these are fine, this is something that we already know, right? And then again for the vapor phase, then it will go on increasing, right? You will get superheated steam and stuff, right? If you think of what. Now, so this is basically the phase change process. This is something that we already know and we have been reading it for quite some time. Now in this process, how does your heat capacity change? Does the heat capacity change or show any change in this process? Now, if I look at that, if you look at different data, say for example, for heat capacity at, so this is basically for sodium chloride, right? Sodium chloride, again, we are looking at solid sodium chloride. That solid sodium chloride melts and then at certain temperature, so Tm here is the melting temperature. Or equilibrium temperature between liquid sodium chloride and solid sodium chloride, you can also call it. So this is the melting temperature, and Tb is the boiling temperature. Now what you know is that you remember that at the solid liquid equilibrium there is no change in temperature, right? You don't see any change in temperature. The thermometer does not register any change in temperature. Again, for liquid vapor, liquid. However, so therefore, as a result, as you can see here, so it is like 1074 Kelvin is for sodium chloride, and this is for and the boiling point is like 2500 Kelvin, where you get the sodium chloride vapor, right? So it is 2005. And now you have basically, so this is the sodium chloride solid, right? NaCl solid. It is like NaCl. The liquid state, the molten state, and here it is like in the vapor. It's gas. NaCl vapor says above the boiling point. Now, as you can see, the variation in Cp is increasing as a function of temperature, and then there is a discontinuity. The idea here, this discontinuity happens at the melting temperature, right? There is a discontinuous change in Cp. There is a, here for example, the Cp has jumped, right? The Cp of solid has changed to Cp of liquid as soon as this transformation has completed. Once the transformation completes, then the Cp of solid has changed to Cp of liquid, which is different. So you can see a discontinuity here. Similarly, you go further down. So here you can see one interesting thing, that the heat capacity of sodium chloride liquid is slightly reducing temperature. And once, again, this is from experimental data, and once you have got this data, now go to the boiling point and immediately you see a change in Cp. The Cp has gone down, right, when sodium chloride from liquid has changed to sodium chloride gas, right? So this is coming from, so by the way, if you want to get all this data for different compounds and different elements, you can visit NIST. This is NIST web book, where NIST stands for National Institute of Standards, National Institute of Standards and I think Technology. So this is called NIST, yeah. So National Institute of Standards and Technology, okay. So you will say, which has this web, which is very nice. So it is in and it's located in Washington DC, Pittsburgh, I think. They maintain this web book where they have all this thermochemical data of different compounds, and you can look at the values of A, B, C, D and all, for different compounds in their solid state, in their liquid state, in the vapor state, and you can plot these, and you will find that one interesting, the important thing that I want to tell, that you will always see, and this is something that is very logical and understandable, that there will be a discontinuous change in Cp, right, at the melting at the transition temperatures. Like this is the melting condition and this is the boiling condition. So you will see a change, right? That is one thing. Now, in general, you will see that, so this is something that you will see, in general, you will have gases will possess lower heat capacity than solids or liquids. Now, why does it happen? So, you think about it, these gases generally have a lower heat capacity than solids or liquids. And remember, this is one thing, when you have a gas phase, even if for a real gas, the interactions are much weaker than in a solid or liquid. In liquid and solid, they are much denser than gas, and so as a result, the amount of interactions the interactions between the molecules will be much stronger when you look at liquids and solids. So as a result, to break these bonds, you will require a much higher amount of heat. So the heat capacity in general, because of the interactions being stronger, heat capacity in general for gases will be smaller than, because in solids and liquids the interactions are much stronger, right? So they have much stronger interactions. As a result, it requires the larger amount of heat to break these interactions, right? So for these different transitions to take place, so they will have, solids and liquids will have higher heat capacity than gases. Now there is one interesting thing, that in some cases you will see that liquids have slightly higher heat capacity than solids. It is also true, the reverse is also true. So liquids often possess slightly higher heat capacity than solids. For example, sodium vapor at 1200 Kelvin. So at 1200 Kelvin is at 1200 Kelvin it will be, I think it is not 1200 Kelvin, it is 1200 C. I will have to check that. So it is basically vapor. We have to check the temperature. This is definitely not 1200 Kelvin. So sodium vapor, so which is above 2500 Kelvin, right? It has to be above 2500 Kelvin. And you see that sodium vapor has a Cp, and has a Cp of 12.47 joules per mole Kelvin. You can check the data from this book and find out at what temperature sodium has this 12.47 joules per mole Kelvin. And liquid has 31.51 joules per mole Kelvin, while solid has 28.20. So as you can see, the Cp of liquid, CpNa liquid is slightly greater than CpNa solid, and is much greater than Cp sodium. Achha, this is sodium, right? So it's not sodium chloride. So yeah, so above 1200 Kelvin, it is correct. At 1200 Kelvin, it is indeed vapor phase, and you get 12.47 joules per mole Kelvin. So Cp of gas or vapor, right? So gases, it is very easily understandable, because gases have much weaker interactions. You don't require much energy to break these bonds. On the other hand, for solids and liquids, you require much higher energy or heat input, and as a result, they will generally possess much higher heat capacity, right? So this is something that is fine. Now, one thing, how to fix the origin? There are two problems here. One is how to fix, what is the origin that I will fix? That is one problem, right? We have talked about, if you remember, Debye's theory of heat capacity of solids, and you will see that at very low temperatures, Debye has this theory where the heat capacity of solids tend to be 0 as the temperature approaches 0 Kelvin, right? So that is one interesting observation, that or interesting outcome of Debye's theory of heat capacity of solids, right? And as a result, for solids at very low temperatures, we use something called a Debye extrapolation, where we assume Cp to be equal to AT cubed, right, at very low temperature. till 0 Kelvin, right? It goes to till 0 Kelvin, right? Again, at room temperature, that at higher enough temperature, again for solids we can use Dulong and Petit's law, right? And then from now it converts to liquid, then we again have to look at how the Cp will change. Now this is Cp by T, right? This is what we are plotting here is not Cp but Cp by T, right? So Cp by T as a function of temperature gives you a characteristic curve like this. So this is a melting point and this is a boiling point. But this is something that I want to tell, that Cp tends to 0. So this is observed even from Debye's theory of heat capacity of solids, that Cp tends to 0 as T tends to 0. Right? And delta S, as you know, is equals to Cp by T dt, just how we have shown. So it is Cp by T dt, this S. So and the integral is between Ti, that is the starting temperature, the initial temperature, and this is the final temperature, right? So STF minus STI is the. So so let us give an example, right? Find its molar heat capacity. So what is this Debye extrapolation and how do we apply it, right? We give an example here. So you have here the problem involves constant pressure, molar heat capacity, okay, or heat capacity. So I am removing this M, but what we are looking at is the Cp denotes molar heat capacity in this problem, okay, because see, it's the molar heat capacity of a certain solid at 10 Kelvin is 0.51 joules per mole Kelvin. Find its molar entropy at 10 Kelvin. Now at low temperatures, Cp of T equals to AT cube and it's valid till 0 Kelvin, right? So Tf equals to 10 K and Ti I will be taking as 0 Kelvin. So Sm, that is molar entropy at temperature T minus molar entropy at temperature 0 is integral 0 to T Cp by T dt, right? Cp by T, Cp by T, and Cp I am using Debye extrapolation, so AT cube by T dt, which is basically a T square dt, which is 1 by 3 AT cube, right? So if you, T square, the integral is T square dt is T cube by 3, so 1 by 3 AT cube. So 1 by 3 AT cubed and Cp is AT cubed, so this is nothing but 1/3 of Cp, right? Because what is the approximation we use? Cp equals to AT cubed. Now the integral gives me 1/3 AT cubed, and instead of AT cubed I substitute Cp. So this is 1/3 Cp. So Sm at 10 Kelvin is Sm at 0 Kelvin plus 1/3 into 0.51, which is Sm at 0 plus 0.17 joules per mole Kelvin, right? So we want to know, so what we require, we have an unknown here. What is Sm of the pure solid, of the solid at 0 Kelvin, right? At 0 Kelvin. So this is something, if we know, then we can tell that Sm at 10 Kelvin is equal to Sm at 0 Kelvin plus 0.17 joules per mole Kelvin, right? Now, if you look at that, the change in entropy, now I know Cp by T and we know ds equals Cp by T dt, so I can also plot the change in entropy. Now, as you can see here, now I have used an origin of 0 and I am telling Cp tends to 0, right, as T tends to 0. I am telling S, so again at T tends to 0, remember that. So and we are using a Debye extrapolation AT cubed, right? So that means at 0 Kelvin Cp is basically going to be 0. So now if you look at S, the change in S, right? So you again see there is a jump in S, right? At delta S melting and delta S boiling, there has to be, right? Because there is a jump in Cp, right? And or jump in Cp by T as well. So as a result, delta S melt and delta S boiling, then there is this. This is like, this is correspond. What does it correspond to? It corresponds to delta H boil by T boil, right? And this corresponds to, right, delta H is basically equal to T delta S, right? So that is what we are understood. So this is delta H boil. So that is basically delta H transformation, right, from liquid to gas. And this is delta H. This again corresponds to delta H transformation from solid to liquid. Right? So this is the change in S with temperature. What we have done here is we have basically extrapolated in such a way that S becomes 0 at 0 point. This, now if I have this curve, then how do I find S? Again, S at T can be estimated at any temperature. T can be estimated this way. S at T equal to S at 0 plus 0 to Tm Cps by T dt. Cps can be a function of temperature. Then there is a delta H by Tm, right, solid to liquid. And then Tm to Tb, there is again Cpl by Tbt. And then delta H liquid to gas by Tb, right, for the boiling point. Again, you have the heat of transformation. Delta H by T is delta S. And then you have Cp gas by Tb, right. So that way we can go to that temperature what we want to find, but we require to know what is Sc, right. So that is something that we want to know, right. So say for example, so you have ds which is equal to dH by T, right, dq equal to dH, dqp equal to tds from second law. So ds equal to dH by heat of transformation. Now think of this transformation. This is a very interesting transformation that actually like tin gray to tin white. This is these are two allotropes of tin. One is gray tin, one is white tin, and this gives you this phenomenon called tin cry. So below 13 degrees Celsius, alpha is stable, and above 13 degrees Celsius, beta, which is white and metallic and ductile, is stable. And so one is metallic and ductile, and another is brittle, right? Gray is brittle. By the way, there is a legend that Napoleon's Russia campaign failed because of this important transformation that took place. The soldiers used to have tin buttons on their uniforms, and these tin buttons, and it's a very cold in Russia, so it's below 13 degrees Celsius. So the tin buttons became powdery and crumbled. So they got affected by very severe cold, and as a result, they could not fight, and they fell ill, and therefore Napoleon's Russia campaign in 1812 failed. So that is one legend that is there. So this is such an important transformation. See one very interesting thing. In this transformation, delta H transformation is plus 2.1 kilojoules per mole, right? It is basically gray to white transformation is an endothermic transformation. Now, if you want to find delta H transformation, what you will do? You will just take delta H transformation equals to delta H transformation by T transformation. But T transformation is basically 13 degrees Celsius, and you can see that it is also positive. Delta H is positive, delta S is positive. You will later see that this gives you a very interesting problem, that delta H is positive, right? So you generally will tend to think that this may not means it may not, because the heat is not evolving, but it is getting absorbed. So that means it requires some sort of a heat to be input, and as a result, it may be a non-spontaneous process. But that is something that we will soon show that this is a possible process, and what is written indeed is correct, and alpha to beta transformation takes place at 13 degrees Celsius, and this is a possible transformation at 13 degrees Celsius, and you get this alpha to beta transformation above. So it becomes beta above 13 and becomes alpha below 13. However, at 13, tin gray and tin white are in equilibrium. This is something that you should know, right? In this case, therefore, the heat of transformation, if you want, you do not involve the heat capacity, right? We do not involve heat capacity when we calculate heat of transformation, because the temperature does not change, right? Now we know about, so one thing I assumed in this curve before, that at S0, if you look at that, I have put a 0 here, right, 0 Kelvin, but for the y-axis I haven't put any value. So I need to find some value, right? So this value will come soon, but before that, we'll just very quickly tell about thermodynamic temperature. Thermodynamic temperature is 1 minus Tc by Th, right? No, this is not thermodynamic temperature. This is called Carnot efficiency. This is called Carnot efficiency, or efficiency of a efficiency of a heat engine, right? Efficiency of the Carnot cycle, right? Efficiency of the Carnot cycle, which is basically which is undergoing this reversible cyclic process, right? So now you see 1 minus Tc by Th. As I told you that we can change either Tc or the Th, and we can vary the efficiency, right? So if I want to make the efficiency equal to 1, I have to put Tc to be equal to 0. Whatever with the Th, if I put Tc equal to 0, because Tc by Th is 1 minus epsilon, or Tc equals to 1 minus epsilon to Th, so put epsilon equal to 1, then Tc becomes equal to 0 Kelvin, right? Here also you can immediately see that Tc equal to 0 Kelvin. So at 0 Kelvin, if Tc is at 0 Kelvin, and if we can have the temperature of the cold sink at which the heat is rejected at 0 Kelvin, I get a Carnot efficiency of 1, right? That's the maximum Carnot efficiency. Now comes, so basically there is a 0 Kelvin at which this dissipation basically is not really there, right? So because efficiency becomes exactly equal to 1, right, in some sense. So that is where comes third law. Again, it's a law that basically gives you the scale of absolute scale of temperature, right? There exists this absolute scale of temperature where the entropy change associated with any physical or chemical transformation as the temperature approaches 0, so goes to 0, right? The entropy change associated with any physical or chemical transformation goes to 0, right, as temperature approaches 0. This is a definition of, this is called Nernst heat theorem, and this is the statement of third law. This is the statement of third law. So Nernst heat theorem comes from this Carnot cycle, right? From this this Carnot cycle, and we can find out that that there is a Tc of 0 Kelvin at which the Carnot efficiency goes to 1, and Nernst heat theorem states that entropy change associated with physical or chemical transformation as the temperature approaches 0 tends to 0, right? It tends to 0. Entropy change tends to 0. So at absolute 0 Kelvin, this is the statement of third law, that at absolute 0 Kelvin, all perfect crystalline substances, so please note this, all perfect crystalline substances, because in material science you have also this other different forms of matter, for example glass, right, which is not really an equilibrium form of matter, but a non-equilibrium form of matter. So remember, at absolute 0 Kelvin, please note, all perfect crystalline substances have the same entropy and it is 0. So S at 0 Kelvin is 0 for all substances in perfectly crystalline form. This important part is perfectly crystalline form, and so at absolute 0, so the absolute 0 is a temperature where all perfectly crystalline substances tend to have 0 entropy, right? They tend to have the same entropy and the same value. The value is basically 0. So it basically tells us, now you remember that it's an SM0. Now if you are looking at SM0, then we can take SM0 to be 0, right? Third law lets us calculate absolute entropies. That's the important part. So I will start from there, from the next in the next lecture I will start from here, and I will also give you the necessary tools to understand equilibrium in thermodynamic systems. Okay.